Welcome everybody. Today we'll be solving Leetcode 2290, minimum obstacle removal to reach corner. So we're given a two-dimensional grid here with values of either 0 or 1. A 0 means the cell is empty and a 1 means an obstacle is present. They want us to return the minimum number of obstacles to remove so you can move from the upper left corner to the lower right corner. So for this example here, starting at this left upper corner, if we remove these two obstacles directly to the right, we can reach our path. And this would only require the removal of two obstacles. We could have, for example, gone down 1, 2, and then maybe remove this obstacle here. And we could have reached our goal destination, but that would have required the removal of 3 obstacles. So remember, keep in mind, we want to return the minimum number of obstacles to remove. Let's look at this example 2 here. So in this example, we can actually freely move where there are no obstacles and reach our path. Hence, this result is 0. We don't need any obstacles to be removed. The goal of the problem is not to find the minimum path, it's to find how many obstacles need to be removed minimally so that we can reach our goal. Okay, for this problem we'll be using breadth first search, and we'll be using, more importantly, a key part of the breadth first search is we'll be using what's known as a deck. So let me write that down. Deck is short for double-ended queue, double-ended queue. And one of the values of a deck is that, or one of the values that a deck provides is that we can add and remove elements from front or back in constant time. And that's what we'll be using as we, it's very important that we use the deck while we traverse our grid to reach our destination. And let me show you why. So let me go through this example here, and it'll become clear why it's important. So currently the deck will look something like this. It'll have our starting origin, the upper left corner. And what we'll do is we'll pop off an element from the deck. So we'll always be looking at nodes that are open first. We want to try the nodes that are open first before we try attempting to remove an obstacle. So let's do that. So we'll use a node equals, we'll call the deck D for now, pop left. And then we'll traverse the neighbors, traverse neighbors. So one neighbor is to the right, and that's located at same row, first column. But notice that has a value of 0. There's also another neighbor for this current node, which is 0, 0. That has a value of 1. That's located at row 1, column 0. So what we'll be doing is we'll be adding the empty nodes to the front of the deck and the obstacles to the back of the deck. And then notice how we're always focusing on the empty cells that have no obstacles first. So in this case, our deck would now look like this: 0, 1, 1, 0. Remember, originally our deck looked like this, but we popped the node off because it was an empty cell, and it was just the cell that was most, it was first. That's where we're starting from. And now we'll do the same thing. We'll pop off the node again. So let's do that. So these are the steps that are going to be crucial. So let me indent this over for a moment, just to make it clear. So in this case, let me just make a comment here. This will be have been 0, 0. This will be 0, 1. And we'll do the same thing. We'll look at the neighbors. So in this case, so we'll need to, we don't want to go back here because this origin is a neighbor of this cell here. So we'll use a visited grid to keep track of the cells we've already visited. So this cell here, again, it has 2 neighbors to the right and below it. So what we'll do is, this is same row but different column. This neighbor is below it and on the first column. So again, we're going to add elements to our deck here. So our deck, so we've popped this element, so that doesn't exist anymore. And we'll be adding the 0 to the front. So let's do that. So 0 to the front. And we'll add this, anything with a 1 to the back. Anything with a 1 to the back. And that's basically what we'll be doing through the entire algorithm, is adding anything with an obstacle to the back and anything that's clear to the front. So that's pretty much it. I'm gonna start coding the problem now. Okay, so let's do it. First thing we want to do is keep track of the number of rows and columns. Let's make it a little bit smaller. No, maybe not. And then we'll keep track of the directions. Okay. And then we'll have our deck. I'll just call it maybe I'll call it Q. And the first element in our deck will be 0, 0. Okay. And we'll also keep track of visited, and visited will be the same size as the grid. And we'll just for now we'll just place maybe zeros and ones, or maybe false and true. So let's do that. So so we'll just put false, and it hasn't been visited, times the number of columns for okay. And let's place visited, let's initialize our first value, so 0, 0 equals true. Okay, so that's for our starting cell. And let's keep doing this until our queue is empty, or we've reached our target, our destination. So what I'll be doing though is, in our queue here, I'll also store the number of removals. So let's write that down here. So this will be row, column, and maybe we'll call this I guess cost. No, we'll just call it removals. Okay, it's fine. So when we pop, when we call q.pop left, this will give us our maybe our node, sorry, our row, column, and removables. Okay. Now we'll check if we've reached our destination. So I've already used row and column here, so let's go back. Let's just maybe call this this. So if okay. Otherwise, we'll loop through all of the neighbors. Sorry, all of the directions for the neighbors. So let's check that. So for dr dc inders, and we'll call this. So let's figure out what the new row and column are. The new row and column would be the current row plus the we'll call it the delta r. Okay. And we'll want to check if this row and column are within the bounds of the grid first. So if and we want to make sure that we haven't visited the cell before, and maybe so not. Okay. So now that we're in here, let's indicate that we have visited this cell. So now we're here. So let's indicate it. It is visited. And remember though, we need, depending on the value of the cell, we need to append it to the front or the back. So if g of r c, so if it's 1, which is just true, but we can make it clear. Let's just call it 1. It's fine. If it's 1, then we'll add it to the back of the queue. Remember that? If it's 1, we want to use it later. We want to use the open cells first. So let's do that. So let's do what is it? D dot append, and we'll append the row column and the current cost plus 1. So the cost, or sorry, the number of removals plus 1. Else, we'll do d dot append left. I'm not sure of the syntax. I think it's left. Let's see if that works. I'm not sure if it's a capital F, capital L, or lower case L, but we'll find out soon enough. R column, and since this is an open cell, we don't need to adjust the removals. And then that should be it. All right, let's test it out. Let's maybe minimize it a little bit, and let's. D is not defined. Oh, what did I do here? Oh, sorry. Okay, looks good. Let's submit it. Okay, looks good. So let me just go over one thing that's important that we did. Was it was important that we used the double-ended queue. That was the whole crux of the problem. When you're solving these algorithms, if you want to pick the most appropriate data structure that will allow you to be like efficient, or maybe even simple. Sometimes a data structure may add complexity, and it's up to you if you want to use it or not. But in this case, it made more sense to use a double-ended queue. And we could have used a list, but in fact, we could even try using the list just to see how it looks. So let's just try that for now if you want. So let me, just in order to demonstrate. You can probably stop watching the video if you want, but let me just go over for educational purposes. If we had tried using a list, so let me just still call it a queue, but I'll just call it, I'm not going to use the deck here, and let me just comment it out for the moment. And let's just use a traditional list. So 0, 0, 0. And then what else here? So for a, we can still append here with no problem, but there is no append left on a list. I think we'd have to do something like insert, insert, and we have to insert it at the index 0 and that. And I think that's everything else. Oh, there is no pop left here. We would have to, what is it? So we'd have to do something like, so this would be Q0. And then we need to adjust Q. So it would be Q equals q starting at 1. I think that's how you would do it. So yes, that's how you would update the queue. Let's just check it locally. So notice it still works as it should, but when we submit it, it should be drastically slower. It might even be time limit exceeded. Yeah, so it's taking longer. And as I mentioned, it might be time limit exceeded. Yeah, it's still submitting. Yeah, exactly. So again, that was the benefit of using the double-ended queue, is that we could, yeah, exactly. So I hope I made my point, and we should try to use the best data structure for any problem that you're doing. So the more you do these problems, you'll become familiar with more and more data structures, and that will, like, allow you to be optimal or be efficient. I did try solving this problem using Dijkstra's, and with Dijkstra's, I used a heap, and again, that was using the heap versus the double-ended queue. The double-ended queue was allowed me to solve the problem faster. So that's why I just decided to present the solution with the double-ended queue. If you would like this to see the solution with using Dijkstra and the heap, comment and just leave a comment, and I'll get to it. But other than that, I hope you learned something. Leave a like, subscribe, and have a great day. Take care.